Good afternoon, everybody, and good evening to our friends in Europe who are joining in today. Today we have a very exciting talk from Rachum on emergent dominance hierarchies in reinforcement learning agents, which is also an AMAS 2024 paper. You'll find the details also in our website. Very exciting work. Ram is an AI safety researcher at Bar-Ilan University. Ram is interested in exploring the use of social behavior in multi-agent RL environments for AI safety goals such as the AI interpretability objectives and AI corrigibility. Ram has spent most of his career working as a software engineer, most recently at Google. He is a recent contributor to open source AI ecosystems, and he's also a fellow at the Python Software Foundation. Further research of Ram can be found on our website. Without further ado, Ram, looking forward to learning more about your very exciting research.
Awesome. Thank you, Saptarashmi. So hi, everyone. Thank you for coming to my talk. This is going to be a talk about our research, emergent dominance hierarchies in reinforcement learning agents. Do feel free to interrupt me during the talk if you have questions. And also, there will be a few points in the talk in which I'm going to ask you questions, so feel free to unmute yourself and give me any answers. We've got 3 links on this slide for the slide deck, the paper, and the code. So yeah, this research was funded by the Association for Long-Term Existence and Resilience, ALTER, and it was accepted as an extended abstract to Amos. And I'm excited because I just bought my tickets to Amos. So in this talk, we're going to talk about aggressive behavior between agents. We'll talk about detaching an agent's behavior from the agent, and we'll talk about cultural evolution and social learning. I want to tell you first a bit about myself and my research mission. So as Saptarashmi said, I used to work as a software engineer. I'm new in the research world. I worked in various companies and I was active in the open source Python community. Now I'm doing research trying to apply multi-agent RL to AI safety at Bar-Ilan University. I'm making this career change because I found this very interesting research mission. I'm going to try to describe it in a few words. I'm interested in the way that humans sort of work together. I mean, the fact that you can take a few humans, and put them in a group, and they are different, and they have different opinions about things, and they get into conflicts with each other, and they have intrigues, and they can become a group of people who work together towards a common goal in a way that is they can achieve more as a group than each of them could achieve as individuals. That is something which I think is the most interesting phenomenon in the universe. And whatever kind of secret sauce is happening there that we don't completely understand, I want to see if we can make that happen with AI agents, and specifically reinforcement learning agents. And I think that if we could get it to happen, this might be sort of like the missing piece or a breakthrough in AI, and especially in AI safety, in the endeavor to make AI systems that we are able to understand why they're doing what they're doing, and we're able to tell them, let's do something a little bit differently. So I'm interested in collective intelligence, and this paper is going to be one modest step in the direction of collective intelligence. This paper is a synthesis of multi-agent RL with the study of dominance hierarchies in animals. Let's talk about the study of dominance hierarchies in animals. So now we are not in the AI world, we are in the biology, zoology, ethology world. Dominance hierarchies, if you've heard the term alpha male or alpha female, this is the field from where this term comes. Dominance hierarchy researchers study the way that animals in a pack, in any group, they sort of organize themselves in a way that there is the top animal, the alpha, who tends to be more aggressive towards all the other animals. And then there's the second in command who's aggressive to all the animals except the alpha, and then the third and the fourth, and so on. This research field was founded by a zoologist, a Norwegian zoologist called Kjell Peebe in 1922, so a bit over 100 years ago. He studied dominance behavior in chicken, and he wrote a paper. He founded the field. Many other researchers in the 100 years since have studied dominance hierarchies in many other animals, linked the dominance behavior to the animal's health, learned how to make living conditions for animals that reduce aggression, and studied many other different aspects of this phenomenon. If you would like to know more about dominance hierarchies, this picture on the right is the front matter of the centennial issue of the prestigious journal Philosophical Transactions of the Royal Society B, dedicated completely to dominance hierarchies. So it has around 10 different papers on different aspects of the field. I recommend it. I want to talk a bit about the way that dominance hierarchy researchers present or visualize their data about how animals are aggressive to each other. I'm going to do a little bit of how it started versus how it's going. So here's how it started. We've got two visualizations here from papers from the 30s and the 50s. Let's look at the left visualization. We have two tables, and the way to read these tables, like looking, for example, at the bottom table, is that we have a bunch of animals, chickens, numbered from A to N. And the number 4 that's circled there means that the animal H has attacked animal E 4 times. So this table basically has data of how many times did each animal attack each other animal. So now attacking looks different in different animals. Chickens would peck each other. A mouse can bite another mouse. So that's the left side of the slide, and the right side of the slide is that these animals, dominance hierarchy researchers, they visualize these aggressions as a directed graph with nodes representing individuals and edges representing dominance relationships between individuals. This is interesting because it allows us to view the structure of the society in a way that's disconnected from the animals themselves. Here is another visualization of dominance hierarchies in monkeys. This is the paper from the 50s. This slide doesn't really contribute to my point, but it's still very cute, so I decided to include it. Here's how it's going. This is a modern interface for exploring dominance hierarchies in groups of chicken and also fish. There are multiple species there. You can actually play with this one. There's a URL at the bottom. It's web-based. You can just load it up right now if you want it. So this is modern, but it has basically the same kind of directed graph. You see it at the top, where the nodes represent individuals. This notation below it. Oh, sorry, I'm hearing an echo of myself. Could thanks. This notation just below the directed graph, I think that's called a musical notation, in which each colorful arrow means one aggressive interaction between one individual and another. So at this point, one possible question is, why do we even care about this? Why does it make sense for us to study dominance hierarchies and try to connect them to multi-agent RL or any other kind of AI? So from the outset, many of the technologies, or well, not many, but important technologies that we use in machine learning have been inspired by natural behavior. The neural networks that we use have been inspired by neural networks in animals and humans' brain. We use reinforcement learning, which is based on operant conditioning, which is the way that animals learn. So it would make sense tentatively that this kind of natural behavior that's prevalent in most animals, dominance hierarchies, it is possible for it, conceivable for it to be useful for us. Specifically, there have been a few works recently, like Microsoft Hologen and Google DeepMind Concordia, that have taken multiple LLMs or multiple multi-model foundation models and put them in a sort of hierarchy with each other that is inspired by hierarchies in human organizations. Like sort of like we got here, commander, writer, safeguard, or any kind of like manager, employee, expert, assistant, or whatever. And having these LLMs talk to each other and sort of have a back and forth about the solution that they are working on for the human operator, it is seen as something that could be useful. It's possible that this back and forth could be more useful than a single LLM or a single multi-model foundation model. And it's possible that studying these kinds of hierarchies that form would allow these hierarchies of models to work better. I do want to give one more disclaimer before I dive in. So this work is pretty basic on the RL side. I'm just going to use one RL algorithm, and I'm not going to modify it in any way. This what's interesting in this work is the synthesis between multi-agent RL and the study of dominance hierarchies, taking their terminology and ways of thinking about agents. There aren't any new algorithms or methods here. There isn't like an obvious here's you can take this and do that. No, it's just a sort of synthesis work. Okay, let's put everything aside, and I would like to do a thought experiment with you. Let's have two reinforcement learning agents play chicken against each other. I'm going to remind you the rules of the game of chicken. We've got two agents. It's a bit like prisoner's dilemma in the sense that we have two agents that are symmetric, and each of them has two possible actions, and one action is nicer and one action is meaner. And the nice action is called dove, and the mean action is called hawk. And if an agent plays hawk and if one agent plays hawk and the other agent plays dove, then the first agent gets 5 points, which is the maximum number of points. So each agent wants to play hawk and it wants the other agent to play dove. But if both agents play hawk, then both agents lose 5 points, which is the worst possible outcome. This means that while an agent does want to play hawk and it wants to have the other agent play dove, if it knows that the other agent is going to play hawk, it would rather play dove and lose just 2 points instead of playing hawk and losing 5 points. So this game has two pure strategy Nash equilibria, which are hawk dove and dove hawk. Okay, now I want to open up this question to you. Feel free to unmute yourself and answer. Let's say that we have these two agents and they are playing chicken against each other, and each of them has a PPO. They're learning with PPO, and they're learning separately, and they are playing this game with each other over and over and over again. What kind of behavior do you think these agents are going to learn? Someone is writing in the chat. Or not, I don't know. Wrong answers are acceptable and encouraged. I won't let you off the hook. Someone's gonna have to take a guess, even if it's an unlikely guess. Okay, maybe I should sort of like. Okay, if I once said conflictive, I don't understand what that means. So the agents, okay, so maybe I haven't explained this properly. So the agents are playing a game. They can either play hawk or they can play dove, and they're playing over and over again. And if I would let them learn for a while with PPO, they're playing against each other. What am I going to see? Am I going to see agents that are always playing hawk with each other, or hawk dove, or dove dove? Are they going to alternate? What's going to happen?
Are they going to always hawk?
Both of them playing always hawk? Yeah. So right.
There should be kind of like a collaboration, basically, but it should be like it's kind of like an alternate behavior in that case. Like one agent is observing and the other agent is currently coming up with an optimal.
It's too difficult for me to hear you, so I'm sorry. But I will answer the previous. Actually, we had two suggestions here. Someone said they're going to play hawk. Someone said they're going to alternate. So I've been having fun asking this question to lots of different people as I was working on the research. Right, and I got lots of wrong answers, even from people who are full-time multi-agent researchers. So a few of the wrong answers would be that some people say agents to play dove all the time, and some people say agents going to play hawk all the time. Now both of these results are not possible, because if both agents are playing hawk all the time, then each of these agents is now incentivized to play dove, because if both agents are playing hawk, they are both losing 5 points. Whichever agent moves to dove, starts losing 2 points rather than 5 points, so they're going to move to dove. And for the same reason, both agents playing dove is also impossible, because then one of them would move to playing hawk, and then that one is going to get more points. And alternating is also, it also won't happen, but I guess it's a little bit complicated to understand or explain why. Another wrong answer I've been getting, this is the premium quality wrong answer, is agents will play dove a certain percentage of the time, and then they would play hawk a complementary certain percentage of the time. Now, the person who answered this answer is obviously going for the mixed strategy Nash equilibrium. However, this answer is not possible. It's not possible for the agents to converge to this solution. Does anyone want to suggest why? Okay, I'll just show you. Even though it is a Nash equilibrium, it is an unstable Nash equilibrium. There is some randomness in the system. So assuming that you get the two agents to converge on this sort of mixed strategy Nash equilibrium, if one of the agents would play hawk just a little bit more than the equilibrium because of randomness, the other agent would be incentivized to play just a little bit more dove. And then the first agent would be incentivized even more to play just a little bit more hawk. And then you'd quickly end up with the first agent playing hawk all the time and the second agent playing dove all the time. Now, and I'm going to show you the actual results. Before I show you the results, I'll introduce you to the metric that we'll use to show the result. The metric is called aggressiveness. A nice fancy definition. It basically means how often the agents play hawk. So aggressiveness is going to be a number between 0 and 1, where 1 means the agent is always playing hawk, and 0 meaning the agent is always playing dove. So now we're going to see a plot of the two agents. It's going to be two lines, one line per agent, showing how they change their aggressiveness over time. They're going to start at an aggressiveness of 0.5 because they get initialized randomly, and then they gradually learn. So this is what happens. We've got agent 0 learning to play hawk all the time, converging to that, and agent 1 learning to play dove all the time. Here is another run of the same experiment. This time agent 0 learned to play dove and agent 1 learned to play hawk. Here is another run of the experiment. Right? If we personify the agents here, we can say that in the first 20 generations, they had a sort of a dominance struggle, and eventually agent 0 came up on top. By the way, I remind you, if you have any questions or anything is unclear, or feel free to interrupt me or raise your hand or whichever way you want to do it. So it is interesting here how we have this experiment that can converge to two possible states, and it is pretty indifferent about which state it's going to converge to, because basically whichever agent gets a little bit of an advantage over the other agent goes all the way to the top, plays hawk the entire time. So this experiment is really indifferent about which of the two possible states it will converge to. Once it converges, it never changes back to the second possible state. So this reminds me a little bit of the concept of a flip-flop in electronics. The fact that we have a sort of component here that can be in two possible states, and what it knows to do is to save the state that it's on. And I'm going to ask you a more complicated question. Let's do the same experiment, but with 6 agents. Now, Chicken is a 2-player game, so I have to explain how we're going to have 6 agents play a 2-player game. And what we're going to do is this. On every turn, on every game, we're going to pair these agents randomly with each other. They're going to play a game of chicken. And they're going to earn points, lose points. And then on the next turn, they will be paired with a random other agent, and they're going to play the game again. Crucially, the agents are able to observe which agent they are playing with. So right now, agent 3's observation is that it's playing with agent 5. Agent 2's observation is that it's playing with agent 4. We invented this game. We call it Chicken Coop, and we got code for this game online. You can run it, tweak it, play with it. Now I'm opening it up to you again. What do you think the agents are going to learn in this experiment? Right? If you run this experiment, we got 6 agents, each of them learning with PPO, playing the game over and over and over again. What kind of behavior do you think we are going to see in those agents? No one wants to guess?
Maybe you'd see something similar to the last experiment where for each pair, one of them will become passive and aggressive. But I would guess that the agents that are passive in one pairing are more likely to be passive in another one, just because it's easier to learn that than to learn like a different policy depending on the opponent you're playing.
Yes, this is correct. You did explain it more on the individual level and not on the group level, but it's good. Now you left something for me to say. I do want to point out one wrong answer. So I've been having fun asking this question as well to many people. And one of the wrong answers I get when I ask this question is that some agents are going to learn to play Hawk and some agents are going to learn to play Dove. So this is wrong. This can't be right. Why can't it be right? Because what happens if 2 agents that play Hawk play with each other? Right? One of them is going to have to play Dove. So now I'll show you the results. So it would be a similar kind of plot. We have the 6 lines for each of the 6 agents, except now the aggressiveness is sort of average over all the other agents that each agent is playing against. And the result looks like this. Got the 6 agents converging to values that seems to have equal spacing between them. At this point, this might remind you a little bit of the plot in the bottom part of the slide of that dominance hierarchy program. Right? It's not exactly the same because their plot's y-axis is rank, while ours is aggressiveness, but it is similar. So here's that run again, and we see that agent 0, the blue agent, is the least aggressive. It's never playing Hawk. And the purple agent 4, is always playing Hawk. Let's look at another run. This is another run. It has the same structure, even though it has a completely different order of agents. So it seems like the order of agents is completely arbitrary. Here is yet another run. Here something interesting is happening, but let's save that for later. Before I'm going to talk exactly about what's happening here, I do want to say that we wanted to have a sort of metric to measure how strongly these agents converge to their behavior. And the problem is because of this, in the way that this experiment can converge to many different kinds of orders, and we came up with a metric that sort of allows us to show that it converges over many different runs without being obligated on what it converges to. So we call this metric rapport. And for each of these experiments, we measured the rapport and found that it converges to 1 pretty quickly. But let's get back to this experiment. And we want to understand what exactly is happening in our population. How come they are converging to these values that are equally spaced? So let's zoom in. Let's zoom into 2 specific agents. Just let's choose the orange and the purple agents. Now let's see what's happening in the interactions only between these 2 agents, right? Putting aside all the other agents. So yeah, this is what happens. Basically what Ryan said. Each pair of agents sort of decide for themselves which of them is going to play Hawk and which of them is going to play Dove. In this case, agent 1 is always playing Hawk to agent 4. Now let's take a definition that's used in the animal world and apply it to our agents. Let's define a dominance relationship between 2 agents, basically saying if one agent is consistently playing Hawk to another agent, meaning it plays Hawk more frequently than a certain threshold. Let's say that agent I dominates agent J, that they are in a dominance relationship where we are modeling this as a mathematical relation, like an arrow from I to J. We can represent it as an arrow from 1 to 4. So this is starting to look like the directed graphs in the PECBIS program. And now we can apply this relation to all of the agents in the population. We can say, let's define a dominance hierarchy as a complete directed graph in which agents are represented by nodes, and the dominance relationships are represented as directed edges. So our population looks like this. Previously, we looked at 1 and 4. 1 dominated 4, and we basically have a bunch of agents, and each pair of agents is as one of them is a dominant and the other as a subordinate. And this is the cause of the plot that we've seen before. Now, this way of representing dominance hierarchies, it's difficult to look at. It's a little bit tricky to understand what's happening here. We came up with a nicer way. This is how we represent those dominance hierarchies. So this was you may be wondering, okay, you just made it linear. How could you do that? I mean, this was like a degenerate directed graph that basically, first I should explain this visualization. This double arrow basically means everything that on the left side of the double arrow is dominating everything on the right side of the double arrow. So this means not only 1 dominates 4, but 1 dominates 3, and 0 dominates 4, 0 dominates 3, 5 dominates 4, etc. And this is true for each and every one of the double arrows. I'm going to talk more about this visualization. First, do we have any questions on anything that came up so far? Good. So at this point, you might be asking yourself, why is this interesting? So this dominance hierarchy structure, it is pretty simple. We definitely didn't need PPO for that. But why is it still interesting? First of all, this behavior was completely emergent. So the fact that we have agents that have sort of come up with a way to organize the population in a way that is stable, this happened without the agents caring at all about the stability of the population or the well-being of anyone except themselves. So the fact that we have a bunch of agents that are completely selfish and only caring about themselves, and the aggregate result of their behaviors as resulted in stability for the group, that is something that is interesting. Now, these kinds of dominance hierarchies are a population level memory. I've said before that for the case of the 2 agents, they function a little bit like a flip-flop, as in they're saving 1 bit. Here we are saving more than 1 bit. So we have these agents learn something, a dominance hierarchy as a population, and now all of them remember this dominance hierarchy, and each of them remembers a different part of it. So the fact that we can have a sort of shared culture to a group of agents, that is interesting. It is also interesting that the agents decide on the dominance hierarchies collaboratively, meaning it's not like one single agent. Not even the top agent decides what the dominance hierarchy is going to be. Each agent has its say. If I were to replace each agent in the group and run the experiment again, I would often get a different result. So it is interesting that they were able to come up with this artifact, this dominance hierarchy, in a collaborative process. And one final thing that's interesting is that each agent automatically becomes an enforcer of the dominance hierarchy. If any agent, for example here, agent 1, would try to play hawk to agents 0 or 2 or 5 that are above it in the hierarchy, they're going to play hawk back against it, effectively punishing it, and both of them are going to get a low reward. And then agent 1 would learn, I'm not going to do that again. I'm never going to play hawk to the agents that are above me. Okay, so far for why dominance hierarchies are interesting. Let's get back to this representation. So isn't this representation trivial? If a dominance hierarchy is linear like that, why do we even need to represent it as a directed graph? Do you remember this run from before? Sort of different run? Here's what's happening here. You've got a sort of rock, paper, scissors situation at the top of the hierarchy. We've got 3 agents where 0 dominates 2, 2 dominates 1, 1 dominates 0. And this triad is dominating everyone else. So here you can see the difference between a single arrow and a double arrow. A single arrow means dominance relationship, and a double arrow means everything on the left of this arrow is dominating everything on the right of this arrow. So this distinction, there's this distinction here that is studied by animal researchers, and we got linear dominance hierarchies on the one hand, or transitive dominance hierarchies, and intransitive or nonlinear dominance hierarchies on the other hand. So this is something that is well known in animals. It's studied in what affects it, what causes it, etc. And these these triads or these fully connected components, they can appear not just at the top, but at any part of the dominance hierarchy. There could be multiple fully connected components. There could be fully connected components that are 4 or 5 agents, not just 3. Um, and this representation that we had is similar to the one used by animal researchers. Here is an example from a research about fish. Here is a group that is similar to the group that we shown here, where there is a rock paper scissors triad at the top, and then 2 agents below that triad. I do like our representation better. Oops, that's a classic mistake. I went to the end. Sorry. Okay, so we ran our basic experiment 300 times, and we got 248 distinct dominance hierarchies, and only 17 of them were intransitive, meaning that they contain cycles. So almost all of the dominance hierarchies that form are linear and transitive. So one question you could be asking is, how come there are cycles? Why does this happen? It seems like an unstable kind of structure. So this is a wrong question to be asking, because the only reason we have to ask this question is the expectation that the population is aiming to reach a sort of a stability point or something that is an elegant solution. But there is a distinction here between a group level explanation and an individual level explanation. Basically, we have each agent here just trying to do the best thing for itself, and none of the agents are even trying to get the group to a stable state. So because there is no individual level explanation for there to not be cycles, then cycles are just going to happen. A better question would be, how come there are so few cycles? I mean, how come most runs don't end up in cycles? And animal researchers are working on this question. There are many different factors that affect the appearance of cycles in dominance hierarchies. One thing that affects it is bystander effects. So animal researchers make a distinction between winner effects, loser effects, and bystander effects. Winner effects means how does an animal change its behavior after it has won an aggressive encounter with another animal. Loser effects is how an animal changes its behavior after it's lost an encounter. And bystander effect means how does an animal change its behavior once it has observed another animal win an encounter against yet another animal. Right, if I'm animal C and I see animal A beat up animal B, and animal B has beaten me up in the past, I might conclude that I don't want to mess with animal A. In this experiment, we don't have bystander effects, and even still, we still don't have many cycles. Bystander effects are only one factor that affects the appearance of cycles. We did a little study of where in the dominance hierarchy do cycles tend to form, and they tend to form mostly in the middle of the hierarchy. We did a little comparison between our experiment and an experiment done in mice, and we've seen that it has a similar frequency of cycles depending on the position in the rank. Okay, let's talk about what I've talked about so far and what I'm going to talk in the 10 or 15 minutes that I have left. So I've talked about why dominance hierarchies are interesting. I've shown you their emergence in our experiments, and I've shown you how they are similar to dominance hierarchies in animals. I'm now going to talk about a little experiment that we've done showing that the dominance hierarchies require opponent identification. Then I'm going to talk about the most interesting bit, which is the way that agents teach dominance hierarchies to new agents. And then I'm going to spend a few minutes talking about possible future work. Before that, does anyone have any questions about anything I talked about? Okay, good. One thing we're curious about is sort of proving that the agents have to
interrupt. There's 2 questions in the chat if you want to look at those.
Oh, sorry, I didn't look at that at all. Let's look at the chat. Humans and most animals have a sense of fairness and might be upset if one player always takes all the reward, resulting in instability due to perceived unfairness. Are there insights around that? No, our experiment is a very, very simple bare bones kind of experiment. So there have been works in multi-agent in the sort of in the intersection of multi-agent RL and dominance hierarchies in the past, whose goal was to understand animal behavior better and be able to model it, like a sock dome and dome world. And they've and that would be more of a question to them. So no, we don't have any insights for that, and that's not really our goal. Our goal isn't to understand animals better. It is to find this behavior from animals, try to boil it down to the simplest possible environment that it emerges in, and then possibly in future work, seeing how that could be useful. So this is a pretty high level of intelligence, having a concept of fairness. Now, dominance hierarchies, they happen in very simple animals, like very small fish, which I don't know, but I think they don't have a concept of fairness. So it isn't a requirement for dominance hierarchies. Second question: what happens when new agents are added? Added after an existing hierarchy is established. We did not run this experiment, but what you were saying is a little bit similar to the experiment I'm going to show after this one, so stay tuned. Okay, but first I'm going to show this experiment. We were interested in showing that the agents really have to recognize each other for this to work. Meaning there is no way for agents to form dominance hierarchies if they can't see who they are fighting against, right? I can't say I'm above that guy and below that guy if I'm not seeing who I'm fighting against. So I said before that the agents have just one observation, which is who am I playing against? We want to test what happens when we obfuscate, when we remove that observation, and we did it gradually. So we came up with a metric called opponent perception accuracy, which is the number between 0 and 1. All of our previous experiments were done with a 1 accuracy, and we add random noise, and the more random noise that we add is less the opponent perception accuracy is. So for 0, it means that they can't see each other at all. They just see random noise. In which we measured how the rapport changes, basically means how much they converge to dominance hierarchy, depending on the opponent perception accuracy. And these are the results. So there is a definite connection between their ability to establish rapport and their ability to identify each other. Basically, the better that the agents can identify each other, the better that they can converge to a dominance hierarchy. And now for my favorite experiment, the way that agents teach dominance hierarchies to new agents. Here's the experiment that we've done. We've taken one experiment run. This is the experiment run that we've been talking about this entire time. We've chosen one agent in an arbitrarily, agent 1, and we are taking this agent 1. We are throwing away all of the other agents. We are putting this agent 1 in a brand new population, and these are agents that have never don't know anything yet. They are naive. And one modification that we're making, that we are freezing the learning for agent 1. So agent 1 is not learning anymore. It's just behaving the way it learned to behave in its previous population. This is what happens. They form a dominance hierarchy. So you see that the orange line, which is agent 1, it seems confident right at the start. It's starting at it's doing its own thing while everyone else is learning. And the agents do form a dominance hierarchy. And this dominance hierarchy is very similar to the dominance hierarchy that agent 1 came from. So agent 1 has been very effective in teaching the new population the dominance hierarchy that it had previously learned. Now, I'm saying agent 1 has been teaching. There isn't really a teaching mechanism, the action. No, when I say teaching, I mean agent 1 just does its thing, playing hawk to 4 and 3, playing dove to 5 to 0. And all the other agents kind of just align to it and adjust themselves to agent 1. We see that the hierarchy is almost identical, not completely identical. And we did want to have a metric. We wanted to have a measurement for how effectively an agent or multiple agents teach a dominance hierarchy from one population to another. We came up with one that we call dominance hierarchy transmission fidelity, which basically means let's count the dominance relationships and see how many of them have remained the same as they were in the old hierarchy. We ran an experiment where we tried different numbers of experienced agents, having them teach the new population the dominance hierarchy that they've learned. So we've tried it with 0 agents and 1 and 2 and 3 and 4. The 0 is basically our control group because then there are no experienced agents. And we've measured the dominance hierarchy transmission fidelity. So these are the results. The results for 0 is what we expect, around 0.5, which basically means that the new hierarchy has nothing to do with the old hierarchy. As soon as we got one agent that's teaching, we're seeing about 0.7, so 70% fidelity. And with two agents that are teaching, we are hitting 80%, which is a very impressive fidelity. So this is very interesting to us because here we are detaching the agent's behavior from the agents themselves. We've got instead of thinking of a dominance hierarchy as this is the way that my agents behave, I can now treat it as an artifact that the agents have come up with, and they are able to transfer this artifact to a new population of agents, transfer and modify. And we think that being able to transfer and modify an idea from one population to another. Sorry, I lost my headphones for a second. Can you hear me now?
Oh yeah, we can hear you.
Great. So just as I was reaching my crescendo, I was saying the concept of having an idea that is passed from one population to the next and it gets changed and it's passed on, we believe that it's a crucial part of a collective intelligence, which is what we're aiming for. Let's talk a bit about future work, and then I'm going to have some time for Q&A. So our goal is collective intelligence. This has been one modest step in that direction. What can we do to get even closer? One nice thing would be to have the agents actually working on shared goals. Right now, we had the agents fighting each other. Now, when animals do form dominant hierarchies, it's not they don't spend all day fighting with each other. They are doing things together, hunting together. They have a collaboration in the group, which is another layer on top of the dominant hierarchy. So we would like to have agents do that. One possible and attractive way to do that is either with LLMs or multimodal foundation models, connect them in some way to RL agents, such that the RL agents sort of maintain a social structure that's similar to that seen in humans, while the multimodal foundation models do actual real-world work. Another possible direction is to have multiple hierarchies. And let's say you have a population of agents, and they don't just have one big hierarchy, but they have different groups. Each group has its own hierarchy, and each agent could belong to multiple groups, and the agent could move from one group to another if it benefits them. And one possible direction is opponent shaping. I'm very interested in the opponent shaping algorithms coming out of Jakob Verse's lab at Oxford. And one of the things that I want to do is experiment with model-free opponent shaping. If you could have agents, so in opponent shaping, opponent agent is an RL paradigm in which each agent doesn't always only think, how do I change my actions to get more reward, but it optimizes for, how do I change my actions such that the other agent is going to learn to behave in a way that gets me more points. So maybe we can have agents saying, how could I change my behavior to have the other agent want me to be the alpha of the group, which could result in interesting behavior. That's it for me. I see that we have, I guess, I don't know how many minutes, but I'll be here to answer any questions that you have. If you would like to get updates on my research, there is a link to my mailing list at the bottom of the slide. Thank you very much for listening to my talk.
Hi, Ram. Thank you so much. Very exciting talk today. Any questions from anybody? Yes, Swaminathan, please unmute and ask.
Thanks for the talk. So I have a question. I mean, I know this is not a talk on a new algorithm or a new technique, but I can't help but wonder, are there like algorithms which sort of penalize the formation of dominance hierarchies and sort of try to maintain the unstable fairness? Or is there some work going on that direction?
We got the suggestion multiple times. It would have been a good thing for us to do, but we haven't. Yes, it would be interesting to try multiple algorithms, see which of them are more conducive to dominance hierarchies and which are less. But yeah, that's future work.
Yeah, thanks a lot.
Any other questions, please?
Hi, Ram. Thanks for the great talk. That was a lot of the thoughts you showed were really cool to see. I was wondering if you've seen the sort of research direction looking into just on a larger scale, like intransitivity in games. It's like one of the papers I'm thinking of, is the Alpha Rank paper, which kind of used it. Honestly, they had some results that looked very similar to what you were doing here, where they sort of constructed this dominance hierarchy of agents. Basically, they take data from a matrix game of some kind. They construct this dominance hierarchy, which will have some number of cycles and some number of strict dominance in it. And then they rank agents based on how likely you are to basically choose to play that agent in this dominance hierarchy. So the agents at the top that are in a cycle together will all get some score based on that, and the agents at the bottom that are strictly dominated will get a score of 0. So you'll basically like rank the top whatever number of agents. And it uses a lot of the same ideas that I think you're exploring here.
Yes, you talk about the spinning toss paper.
There's that one too, yes. Do you remember the title of that paper? Because I've tried to find it and I forgot what it was called.
I know the spinning tops one. I don't remember the title. It just has spinning tops in it from DeepMind. So you were saying there is another paper that's
there's another paper that's called Alpha Rank. It's basically a ranking algorithm based on these intransitivity cycles within games.
I didn't know about that. We did mention and cite the spinning tops paper because yes, it is very similar and it is very interesting and a unique paper. But I haven't seen Alpha Rank, so I'm going to check that out. Thank you very much.
Okay. Yeah, I think you'll see a lot of similar ideas there. So I'm hoping there's some connections to your work. But thank you for the talk. This is super cool.
Awesome. Had a good time. Thank you everybody for coming.
Sure. If there are no other questions, maybe today we're really excited to know about this dominance hierarchy stuff now. And we look forward to the participation next week too, when spring break will close, and we'll have Ian Gemp from Google DeepMind essentially would be talking about his research on approximating Nash equilibria in normal form games essentially. So based on like Ram stuff today about stable Nash equilibrium stuff, it would be like a very nice extension from Ian's ICLR 2024 paper, and the other talks from our friends at Google DeepMind, my mentor at Harvard, Professor Leslie Valiant, and also from Costa in a Hugging Face will be very soon. So looking forward to those talks and participation. Thank you so much for joining in, and have a wonderful rest of your weekend. Bye-bye.
Have a great day.